Hey everyone, and welcome. Today we are tackling one of the most profound and, honestly, one of the most beautiful ideas in all of science, Stephen Hawking's incredible proposal for how our entire universe might have begun.
I mean, it's the biggest question there is, right? For as long as we've been human, we've looked up at the sky and wondered, how did all this get here? The galaxies, the stars, us. Where did it all come from? For a long, long time, the Big Bang Theory was our best shot at an answer. But it came with this giant glaring problem right at the start. A moment called a singularity, where all the laws of physics as we know them just completely fall apart. But what if we've been thinking about the beginning all wrong? What if the universe is finite, but it has no starting point, no edge in time? Okay, so to really get why Hawking's idea is so revolutionary, we first have to understand the massive headache that the Big Bang singularity created for physicists. A singularity is basically a dead end. It's the point where our understanding of the universe just hits a brick wall. Imagine a point where gravity becomes infinitely strong, where space and time are infinitely warped, a point where all the equations that describe our universe just give you nonsense answers. It's not just a moment in time, it's supposedly the moment time itself began. And this wasn't just some wild guess. Back in the 1960s, the brilliant Roger Penrose and Stephen Hawking himself proved that this singularity wasn't just some weird possibility, it was an absolutely unavoidable prediction of Einstein's theory of gravity. If you take our expanding universe and just run the clock backwards, you are forced to end up at this point. And this wasn't some kind of theoretical fluke that only happens in perfect models. Oh no. The Penrose-Hawking theorems showed that pretty much any universe that looks like ours has to have started from a singularity. And that meant, according to classical physics, time itself had a hard, sharp edge, a beginning. So how in the world do you solve a problem like an infinitely dense point where physics breaks? Well, Hawking, along with his partners in crime, James Hartle and Thomas Hertog, came up with a truly radical and, frankly, elegant solution. What if you just get rid of the edge? This is the big idea, the huge conceptual leap. Instead of picturing the universe starting at an infinitely sharp point, like the tip of a cone, imagine it starts as a smooth, curved cap. No point, no sharp edge, just a smooth beginning. And when you put them side by side, the difference is just night and day. The singularity model gives us a universe with this hard starting line, an edge of time that, metaphorically, you could fall off. But the no-boundary model? It describes a universe that's totally self-contained. It's finite in the past, sure, but it has no boundary, no edge, and absolutely no singular point where it all kicked off. Hawking came up with this brilliant analogy to explain it. Think about the North Pole on Earth. It's definitely a special point. It's the northernmost point, right? But there's no boundary there. You can't fall off the edge of the North Pole. In the exact same way, the beginning of the universe could just be another point in space-time, a point where the rules change, but they don't break. Okay, so how do you actually do that? How do you mathematically take that sharp, pointy beginning of time and just smooth it out? Well, this is where the physics gets wonderfully strange. The key is a mathematical concept called imaginary time. Now, it's super important to note that imaginary here doesn't mean made up or fictional. It refers to imaginary numbers, like the square root of -1. By using this mathematical tool, the theory shows that way back in the earliest quantum moments of the universe, the dimension of time essentially behaved just like another dimension of space. It's the mathematical trick that lets you round off that sharp beginning. And this gives us this amazing picture of the universe's geometry, often called the shuttlecock model. Imagine it. At the very bottom, that smooth, rounded cap, you've got a four-dimensional space. No time at all. Then, as you move up from the bottom, one of those space dimensions smoothly transforms and becomes the time that we all experience. And from that point on, our familiar universe of 3 space dimensions and 1 time dimension just expands outward. But hang on, because this quantum beginning doesn't just give us one history for our universe. Oh no, it kicks the door wide open to something much, much bigger, a multiverse of possible pasts. So this idea comes from a cornerstone of quantum mechanics, developed by the legendary Richard Feynman. He figured out that to predict where a tiny particle is going to end up, you can't just assume it takes one single path. No, you have to account for every single possible path it could have taken to get there, all at the same time. So what the no-boundary proposal does is take that exact same logic and apply it to the entire universe. Think about that. It suggests our universe didn't follow one single fixed path from its beginning.
Instead, it exists as a sort of quantum combination of all possible histories that started without a boundary, which means the past, just like the future, is a landscape of possibilities. And what's so incredible is that the theory actually lets us calculate which of those possible histories are the most likely. And it turns out that universes that go through a short burst of super fast expansion, something we call inflation, are by far the most probable outcome. And that lines up perfectly with what our telescopes tell us about our own universe's history.
Now, I know what you're thinking. This all sounds like some pretty wild, mind-bending philosophy. But is it actually science? I mean, can you really test a theory about what happened before the Big Bang?
The answer is a resounding yes, and that's what makes it so powerful. A real scientific theory has to make predictions that we can go out and check. If what we see in the sky doesn't match the predictions, then the theory's wrong. Simple as that. And the no-boundary proposal makes several of these testable predictions.
And here's the amazing part. When we look out at the cosmos, the predictions line up beautifully. The theory says inflation is highly probable, and that perfectly explains why our universe is so huge and so flat. It also predicts that there should be tiny quantum jitters left over from the very beginning. And guess what? We've seen their imprint, clear as day, in the faint afterglow of the Big Bang. We are literally seeing the seeds of galaxies that the theory predicted would be there.
In the end, what the no-boundary proposal gives us is a picture of a universe that's self-contained, it's elegant, and it's born from the laws of physics themselves, without needing some special creation moment outside of those laws. And as Hawking himself so beautifully said, this boundless vision of the cosmos really reflects a powerful truth about us, that our own search for knowledge, our own human endeavor, should also have no boundaries.